Welcome back to our flipped classroom, and today we start talking about the formation of compounds, and we're specifically focusing on ions and ionic compounds. And so, as our little comic shows, we recognize that oppositely charged ions are going to be attracted to one another through what we call electrostatic attraction. So today what we're learning is how to predict what charge ions are going to have and how to combine them together to make neutral compounds. So we'll start with the first one. How do we know what charge an ion is going to have? And this is where we're going to turn to our trusted periodic table, and we're going to recognize that ions are always going to form so that each atom, whether it's by gaining or by losing electrons, has what we call a pseudo-noble gas configuration, meaning that it has 8 electrons in its outer shell, or 8 valence electrons. So our metals, which have fewer valence electrons, are going to lose electrons to form positively charged cations. And nonmetals, which have more than 4, generally speaking, are going to gain electrons, and they're going to form negatively charged anions. So notice that we're losing electrons to form positive charge. So when we lose something, we become positive because the things that we are losing are negative. And then when we gain electrons, it becomes negatively charged. And so we'll use these terms throughout the year. We'll talk about cations, which are positive ions, and anions, which are negative ions. And we can remember that because cations are positive and anions are a negative ion, so An ion. Okay, so let's take a look at the periodic table and let's learn about predicting these ionic charges. So group 1, which are alkali metals, are going to lose 1 electron and they're going to form +1 ions. So as an example, hydrogen will lose 1 electron and it will have a +1 charge. And same thing with lithium, as well as sodium and potassium. So everything in this group is going to form a +1 charge. All right, so group 2, 2 valence electrons, they're going to lose 2 electrons to form those +2 ions. Beryllium, magnesium, calcium, strontium, and barium. So notice that it's the second column, 2 valence electrons, it's going to lose those 2 valence electrons. Okay, so we're going to skip over this whole middle section here in the transition metals, come back to those. And let's talk about group 13 or group 3A or the boron family. And these, because they have 3 valence electrons, are going to form +3 ions, boron, aluminum, gallium. So we're going to lose those 3 electrons, form those +3 ions. So what about group 14 or the carbon family? They have 4. Are they going to gain them? Are they going to lose them? And the short answer is group 4 elements rarely form ions. Now, with the exception that tin and lead are what we consider transition metals, and so those we'll address when we talk about the transition metals, because tin and lead do form ions, but the other ones, germanium, silicon, carbon, rarely form ions. So now we move to group 15. We know that we have 5 valence electrons. And so here, in order to get to 8, it's going to be easier for them to gain 3 electrons and form ions with a charge of -3. So nitride, phosphide, arsenide. So those are our group 15 ions. All right, moving on to group 16. We know that we have 6 valence electrons. In order to get to 8, they only have to gain 2 and form ions with a charge of -2. So that would be oxide, sulfide, and selenide. And we're going to learn all about the naming conventions in the next couple of days. Okay, so group 17, or the halogens, we know that they have 7 valence electrons. So in order to get to 8, they only need to gain 1 electron. So they're going to form ions with a charge of -1. So that would be fluoride, chloride, bromide, iodide, and we're going to leave out astatine because it's radioactive and doesn't really form ions. Okay, so last one then is going to be, whoops, I skipped one, sorry, is going to be group 18, or the noble gases. And because the noble gases already have 8 valence electrons, they are stable and they do not form ions. So we've covered all of the main groups, groups 1, 2, and then 13 through 18. So let's go back and talk about these transition metals. So these transition metals are the ones in the middle of the periodic table. We'll learn later on that these are the D block elements. And I would include some of the metals under the stair step as transition metals as well. And most of the transition metals can have more than one oxidation state. So we can't look at them on the periodic table and know what their charge is going to be. So iron can have a charge of +2, or iron can have a charge of +3. And there are many, many elements in this area that are the same. And so we'll talk about how to figure out charges on those in a little bit more detail in the next couple of days. However, there are 2 transition elements that only form 1 oxidation state, only take 1 charge. And those that you need to know are zinc, which forms a charge of +2, and silver, which takes a charge of +1. So those are the only 2 transition elements that you're expected to know what their charges are. The other ones are variable. Okay, so now that we know what charge our ions are going to have, let's talk about how we put them together. So a bond is a force that holds groups of atoms together and makes them function as a unit. So when we talk about an ionic bond, what we're talking about is the transfer of electrons, which then results in electrostatic attraction of the opposite charges. The bond is actually the electrostatic attraction, but it has to be preceded by that transfer of electrons. And in covalent bonds, we're talking about the force that holds them together is the sharing of the electrons. So we just said, when ionic bonds are formed, when ionic compounds are formed, ions come together due to electrostatic attraction. So we're always going to have a positive charge and a negative charge. And the net charge on the compound always has to be 0. So for example, if we have the ions magnesium and chloride, we're going to have 2 chlorides for every 1 magnesium, so that each magnesium can lose 2 electrons, each chlorine can gain 1 electron for a total of 2. And so we have a neutral compound and we've transferred the same amount of electrons. By the same token, if we look at sodium oxide, we know that sodium is going to form a charge of +1. Oxygen is going to gain 2 electrons. So it needs to have 2 sodium ions in order to gain those 2 electrons. And we're going to form a neutral compound. And then the last one, and these are the trickiest ones, aluminum sulfide. So we see that aluminum is going to form a charge of +3. Sulfur is only going to form a charge of -2. So we can't put 1 and 1, and we can't put 2 and 1. So what we have to do is we have to have 3 sulfur atoms, each losing 2, or each gaining 2 electrons, and each aluminum is going to lose 3, so that we have a total of 6 lost and 6 gained. Okay, so how do we write ionic formulas? So we're going to learn about naming conventions, as I promised, in the next couple of days. But when we write ionic compounds, we want to make sure we write the formulas for the cation and the anion. And we're going to go ahead and include those charges. So barium nitrate, barium is a +2 ion, nitrate is a -1 ion. We're going to check and see if those charges are balanced. And we can see that barium is +2, nitrate is -1. That is not balanced. So we're going to add subscripts to our ions to balance those charges. So we need 2 nitrates to go with our 1 barium. Since nitrate is a polyatomic ion, we're going to put it in parentheses, and we're going to put that subscript 2. Now, when we write this, we're going to get rid of those charges. So this would just be Ba parentheses NO3 and parentheses 2. Okay, so when we're practicing writing them, we're going to put the charges in, but when we write our final formula, we want to make sure that those charges are erased. Let's just look at a couple more examples. So we're going to look at ammonium sulfate, again, writing the formula for the cation and the anion. And so our formula for ammonium, we can see that it is a +1 charge, and sulfate is a -2 charge. That is not balanced. So once again, because this is a polyatomic ion, we're going to put parentheses around the NH4, and we're going to put a subscript 2 so that we have a total of +2 to go with our -2. Okay, just a couple more. Iron 3 chloride. And this is, we're going to talk about this with the naming convention. That 3 tells us that the iron is a +3 ion. Chloride, we have a -1 ion. So we need 3 chlorides to go with every 1 iron. And we're going to put that subscript on there, and we'll have FeCl3. Okay, last one, I promise. So we're going to use the example of aluminum phosphate. Oh, no, not aluminum phosphate. Yes, aluminum phosphate. Aluminum sulfide, sorry. So we're writing the formulas for the cation and the anion, including our charges. We see that aluminum is a +3. Sulfur is a -2. That's not balanced. So I'm going to use what I call the crisscross rule. And I'm going to take this 2, and I'm going to make it the subscript for aluminum. And I'm going to take the 3, and I'm going to make it the subscript for sulfur. Anytime we have different charges, we can use that crisscross rule, and it'll give us the balanced formula. So 2 aluminums, 3 sulfides, and we wind up with a total of +6 and -6, and we have our neutral atom. And again, remember that we would erase those charges, and we would have Al2S3. All right, we're going to stop there. And as always, if you have any questions, let me know, and I look forward to seeing you in class.